Have you ever looked up at the night sky and felt a sense of awe, not just at its beauty, but at the sheer mystery of it all? We like to believe that the universe operates by rules we can understand, that if we look closely enough, everything will eventually make sense. But what if the cosmos is far stranger, far more bewildering than we ever imagined? What if the very laws we rely on to explain reality are, in fact, full of contradictions that leave even the most brilliant scientists utterly perplexed? We're about to embark on a journey into the heart of these cosmic mysteries, and I promise by the end, you'll see the universe in a completely new light. Think about it. We go through our days assuming that time moves forward, that objects exist in one place at a time, and that cause always comes before effect. These aren't just ideas, they're the bedrock of how we experience life itself. But the universe doesn't play by our rules. Out there, in the vast expanse of space and the eerie realm of the quantum, reality behaves in ways that seem to mock human logic. Particles can be in two places at once. Time might not be a one-way street, and the eerie silence from other star systems raises questions we still can't answer. These aren't science fiction, these are real, observed phenomena that challenge everything we think we know. In this video, we're diving deep into 25 of the most astonishing ways the universe defies human logic. From quantum entanglement, where particles millions of light-years apart can instantly influence each other, to the unsettling implications of the Fermi Paradox, we'll explore concepts that stretch the mind and ignite the imagination. This isn't just a list of facts, it's an invitation to rethink your place in the cosmos. So settle in, open your mind, and get ready to explore the beautiful, the bizarre, and the downright unbelievable truths hidden among the stars. Our journey into the bizarre begins not in the vast emptiness of space, but in the impossibly small world of quantum mechanics. Here, we encounter the first and perhaps most fundamental way the universe defies our logic, the principle of quantum superposition. In our daily lives, we take it for granted that objects have definite properties. A cup is on the table or it isn't. A light switch is on or off. This binary, either-or logic is the foundation of how we perceive reality. But venture into the quantum realm and that foundation completely crumbles. An electron, for instance, does not choose a single location. Instead, it exists in a blurred, probabilistic state of all possible positions it could occupy, spread out like a ghostly cloud. It is only at the moment we consciously observe or measure it that this cloud of possibilities collapses, forcing the electron to choose a single, definite location. This isn't a limitation of our instruments, it is a fundamental property of the universe. The iconic thought experiment that brings this home is Schrödinger's cat. A cat is placed in a sealed box with a radioactive atom, a Geiger counter, a hammer, and a vial of poison. If the atom decays, the counter triggers the hammer to break the vial, killing the cat. But since the atom is governed by quantum rules, it exists in a superposition of both decayed and not decayed states until the box is opened. Therefore, the cat, by extension, must be both alive and dead simultaneously, a state that is utterly nonsensical to our macroscopic brains. Pioneers like Niels Bohr and Werner Heisenberg proposed that this isn't just a mathematical quirk, it is the true nature of reality at its most fundamental level. The act of observation itself seems to play an active role in shaping reality, a concept that deeply unsettles our classical understanding. This profound mystery is no longer just theoretical. It's the very engine behind emerging technologies like quantum computing. Where classical computers use bits that are either zeros or ones, quantum computers use qubits, which can be 0, 1, or both at the same time, allowing them to perform calculations at speeds once thought impossible. This forces us to ask a deeply philosophical question. If reality at its core is undefined until observed, what does that say about the nature of existence itself? It suggests the cosmos is built not on certainty, but on a spectrum of potential waiting to be realized. If you found the idea of superposition mind-bending, prepare to have your entire concept of separation unraveled. This brings us to our second great defiance of logic, quantum entanglement. Picture two particles, perhaps two electrons or photons, created together in a single event. They become intimately linked, sharing a single quantum description. Now, imagine flinging these two particles in opposite directions across the universe, separating them by millions of light years. According to every rule of classical physics we hold dear, these particles should now be independent entities, but the quantum world laughs at such notions. Despite the unimaginable distance, these particles remain mysteriously connected. Measuring a property of one particle, say, its spin or polarization, instantly determines the state of its partner. Not at the speed of light, not through some invisible signal we can detect, but instantaneously. This was so unsettling to Albert Einstein that he famously derided it as spooky action at a distance, believing it revealed a flaw in quantum theory rather than a feature of reality. He argued that there must be some hidden variables, some deeper mechanics we hadn't yet discovered that would restore a sensible, local universe where influences cannot travel faster than light. For decades, this was a philosophical debate. Then, in the 1960s, a physicist named John Bell devised a way to test it. His theorem, and the experiments that followed, delivered a stunning verdict: Einstein was wrong. There are no hidden variables. The spooky action is real. The universe is fundamentally non-local. This result is not just a mathematical curiosity. It has been confirmed repeatedly in laboratories around the world. Researchers have entangled particles and measured their linked states across ever-increasing distances, solidifying one of the most profound discoveries in modern science. The implication is that space itself, the vast emptiness that separates stars and galaxies, might not be the ultimate barrier we believe it to be. Entanglement suggests a deeper, hidden layer of reality where everything is interconnected, a cosmic web where information transcends the physical limits of distance. This forces us to confront the very nature of cause and effect. How can something here influence something there with no time delay and no energy exchanged? It challenges the core principle of locality, the idea that objects are only influenced by their immediate surroundings. Instead, we are pushed toward considering that the universe might be more holistic, more unified than its separated appearance suggests. This has led to revolutionary ideas like the Holographic Principle, which proposes that all the information contained within a volume of space might actually be encoded on its two-dimensional boundary, much like a hologram. If true, our seemingly three-dimensional reality could be a projection from a deeper, interconnected fabric. So what does this say about you sitting there watching this? It hints that the feeling of being a separate, isolated individual in a vast, empty cosmos might be the ultimate illusion. At the most fundamental level, the particles that make up you and the particles at the farthest edge of the observable universe might still be playing by the same entangled, interconnected rules, bound together in a cosmic dance that defies all human logic and redefines our very understanding of connection itself. Just when you think the universe couldn't get any stranger, it delivers its next shocking defiance, targeting the very fabric of our existence, time itself. We all operate under the assumption that time is a universal constant, a steady, unchanging river that flows at the same rate for everyone, everywhere. But this deeply held belief is an illusion. The reality is that time is elastic, malleable, and deeply personal. This is the astonishing phenomenon of time dilation, a cornerstone of Einstein's theory of relativity that shatters our intuitive understanding of reality. To grasp this, picture a simple experiment. Imagine two identical, perfectly synchronized atomic clocks. One remains securely on Earth, while the other is placed aboard a spacecraft traveling at an incredible fraction of the speed of light. Upon the spacecraft's return, when the two clocks are compared, you would find a measurable difference. The clock that journeyed through space would have ticked slower. It would literally be behind its Earth-bound twin. Less time would have passed for the traveling clock. This isn't a mechanical error or a trick of perception. It is a fundamental property of the universe. Time itself passed at a different rate for the moving object. This concept moves from thought experiment to practical application every single second of every day with the global positioning system. Each GPS satellite in orbit is moving at tremendous speeds relative to us on the Earth's surface. Furthermore, they are higher up, experiencing a slightly weaker gravitational pull. According to relativity, both of these factors affect the flow of time. The satellite's high speed tries to slow their clocks down relative to ours, while the weaker gravity tries to speed them up. The net effect is that time on a GPS satellite runs faster by about 38 millionths of a second per day. If the engineers who designed the system did not deliberately program the satellite's clocks to compensate for this difference, the entire network would become useless. The navigation data it provides would drift by over 6 miles each day, rendering turn-by-turn directions completely incoherent within minutes. Our daily reliance on functional GPS is therefore a constant, silent affirmation that Einstein was right. Time is not absolute. Physicists like Brian Greene often explain this by describing the universe not as a three-dimensional stage where events unfold, but as a four-dimensional fabric called space-time. Think of this fabric like a vast, flexible trampoline mat. Massive objects like stars and planets create dips and curves in this mat. That's what we experience as gravity. Now, everything in the universe is moving through this four-dimensional space-time. Your total motion is always constant, a combination of your movement through space and your movement through time. When you sit completely still, all your motion is directed through the time dimension. But if you start moving through space very quickly, like our hypothetical spacecraft, some of that motion must be borrowed from your movement through time. The faster you move through space, the slower you move through time. Your velocity through time literally slows down. This leads to one of the most famous mind-bending paradoxes in all of science, the twin paradox. Suppose one twin stays on Earth while the other embarks on a journey to a distant star at a speed close to that of light. Due to time dilation, from the Earth-bound twin's perspective, time is moving much slower on the spaceship. When the traveling twin returns after what felt like a few years to them, they would step out to find their Earth-bound sibling has aged decades. They are no longer twins. This isn't just a story, it's a rigorous prediction of a theory that has been proven correct time and again. It forces us to abandon the idea of a single, universal now. Your now is relative to your state of motion and your gravitational environment. The past, present, and future may not be the rigid structure we believe them to be, but could instead all coexist equally in the block universe theory, where time is just another dimension, and every moment is fixed in place. We simply experience it sequentially, like a reader scanning a line in a book, unable to see the entire page at once. This reveals that our most fundamental experience of reality, the relentless, steady tick of the clock, is perhaps the greatest trick the universe has ever played on our mind. This perspective completely redefines what now even means. If the past, present, and future are all equally real, then your birth, your first day of school, the moment you're watching this video, and every event yet to come are all fixed points, permanently etched into the structure of the cosmos. This is the block universe theory, and it stands as our fourth stunning defiance of human logic. It proposes that time, as we feel it passing, is not a fundamental feature of the universe, but rather a powerful illusion generated by our consciousness. Think of reality not as a river flowing from past to future, but as a vast, unchanging four-dimensional sculpture, a block of space-time where every event, from the Big Bang to the distant heat death of everything, already exists. In this view, the universe is static. It doesn't become, it simply is. This isn't just philosophical speculation. It's a direct interpretation of Einstein's theory of relativity. His equations treat time as a dimension, much like length, width, and height. When we pinpoint an event, we give it coordinates in space-time, an address that includes not just where but also when. Crucially, the theory shows that two observers moving at different speeds will disagree on whether two events are simultaneous. There is no single, universal now that applies to everyone everywhere. Your present moment is not the same as the present moment for an astronaut on the International Space Station or for a hypothetical being near a black hole. This relativity of simultaneity dismantles the idea of a moving, present moment that sweeps across the cosmos. If there's no privileged now, then all moments must be equally valid and real. The physicist Julian Barber takes this even further, arguing that the entire universe is a collection of frozen, static nows that he calls time capsules. Our brains, he suggests, are simply structured in a way that strings these individual snapshots together, creating the irresistible and persistent illusion of flow, change, and duration, much like a film projector creates the illusion of motion from a series of still frames. The implications of this are nothing short of earth-shattering for how we view ourselves. It challenges the very core of free will. If the future is already out there, a fixed part of the block, then are our choices truly our own? Or is the feeling of making a decision merely us experiencing a predetermined path? It questions the nature of progress. If everything is already written, then the journey isn't about creating a future, but about uncovering a path that is, from a God's eye view, already complete. This can feel deeply alienating and nihilistic. How do we find meaning in a life where our triumphs and tragedies are pre-existing statues in a cosmic museum? The answer might lie in the subjective human experience. While the universe may be static, our perception is not. Our consciousness seems to be a process that moves through this block, illuminating one slice of space-time at a time. Memory gives us access to the slices we label past, and anticipation gives us a shadowy outline of the slices we call future. This journey through the block is what creates our story, our narrative of growth, learning, and change. The meaning isn't in the static arrangement of events, but in our first-person experience of moving through them. The block universe theory doesn't necessarily erase purpose. It simply relocates it from the cosmos to the conscious mind. This leads us directly to another cosmic puzzle that is just as baffling. If the universe is a fixed, four-dimensional structure, why is its initial configuration so perfectly arranged to allow for that structure to eventually include conscious observers like us? The apparent precision of the universe's fundamental constants forces us to confront an even deeper mystery, one that makes the static nature of reality seem almost tame by comparison. Just as we are forced to reconsider the nature of time, we are confronted with an even more profound mystery that seems to suggest the entire cosmic stage was set with us in mind from the very beginning. This is the fifth and perhaps most philosophically charged way the universe defies human logic, the fine-tuning problem. The fundamental constants and forces of nature appear to be balanced on a razor's edge with a precision that is utterly breathtaking. The strength of gravity, the mass of an electron, the precise value of the cosmological constant, these are not arbitrary numbers. They are the bedrock of reality, and they all seem to be dialed in to exactly the right values to allow for the existence of stars, planets, and ultimately, life. Change any one of them by even a minuscule amount, and the universe as we know it would not exist. Consider the force of gravity. If it were just slightly stronger, the universe would have collapsed back on itself in a catastrophic big crunch almost immediately after the Big Bang, snuffing out any possibility of cosmic evolution before it even began. If it were slightly weaker, matter would have flown apart so rapidly that it could never coalesce into the galaxies and stars that serve as the cradles for heavy elements. The cosmological constant, which governs the energy density of empty space and the rate of the universe's expansion, is perhaps the most stunning example. It is measured to be astonishingly small, yet if it were even slightly larger, the accelerated expansion of the universe would have torn everything apart before galaxies could form. If it were slightly more negative, the universe would have collapsed in on itself eons ago. The odds of this constant having the value it does, purely by random chance, are often described as being like throwing a dart from across the universe and hitting a 1 millimeter target on the other side. It is a statistical improbability so vast it defies human comprehension. This incredible precision was formally articulated by physicist Brandon Carter with his Anthropic Principle, and later explored in depth by cosmologists like Martin Rees. The principle simply states that the universe must be compatible with the conscious life that observes it, because we are here to observe it. But this is less of an explanation and more of a statement of the problem. The sheer unlikelihood of this perfect balance forces us to consider explanations that lie far outside the bounds of everyday logic. One possibility is that we are the beneficiaries of an almost impossibly lucky cosmic lottery ticket, a 1 in a trillion fluke that happened to produce a habitable universe. For many scientists, this stretches credulity to its breaking point. This leads to a second and currently more popular explanation within the scientific community, the multiverse. If our universe is just one bubble in a vast, perhaps infinite, foam of universes, each with its own unique, randomly generated set of physical laws and constants, then it is no longer surprising that we find ourselves in one of the rare habitable ones. In this view, the fine-tuning is an illusion of perspective. We couldn't possibly observe a universe that wasn't fine-tuned, because those other universes are barren, empty, and devoid of any observers to wonder about their laws. While this elegantly solves the statistical problem, it pushes the boundaries of science into the realm of the untestable, at least for now. A third explanation, of course, is some form of cosmic design or deeper underlying principle that necessitated a life-permitting universe. Each of these options, incredible luck, a multiverse, or a deeper principle, challenges our conventional understanding of cause, effect, and probability in ways that are deeply unsettling. This fine-tuning mystery connects directly to our search for meaning and our place in the cosmos. It also casts a new light on the Fermi Paradox, the puzzling silence we encounter when we listen for other intelligent civilizations. If the universe seems so perfectly tailored for life, then where is everybody? Perhaps the answer is that the fine-tuning goes even deeper. Maybe the conditions necessary for not just life, but for intelligent, technological, long-lasting life are even more rare and precise than we can imagine. The universe may be hospitable to simple life, but filled with quiet, insurmountable barriers that prevent life from ever progressing to the point of broadcasting its presence across the stars. This fine-tuning, therefore, is not just a curiosity for physicists. It is a fundamental question about the very character of reality, asking us whether the cosmos is ultimately random, designed, or merely one page in an infinite book of possibilities. And this profound mystery of fine-tuning leads us directly into one of the most haunting and enduring questions in all of science, a silence so deep it seems to scream at us from the void. This is the sixth great defiance of human logic, the Fermi Paradox. The numbers are overwhelmingly on the side of life. Our galaxy alone contains hundreds of billions of stars, and we now know that a significant fraction of them host planets within the habitable zone, the so-called Goldilocks region where temperatures are just right for liquid water to exist. With so many potential cradles for life, and given the universe's immense age of over 13 billion years, the cosmos should be teeming with intelligence. The galaxy should be a vibrant, noisy metropolis filled with the signals and engineering projects of countless civilizations. And yet, when we point our radio telescopes to the heavens, we are met with nothing but an eerie, static silence. It is a silence that contradicts every logical expectation based on probability alone. The paradox gets its name from a casual lunchtime conversation in the summer of 1950. The brilliant physicist Enrico Fermi, while discussing flying saucer reports with colleagues, simply looked up and asked, "But where is everybody?" He wasn't just being flippant. He was pointing out a profound contradiction. Even with conservative estimates and assuming slower than light travel, the Milky Way galaxy could be completely colonized in a few tens of millions of years, a mere blink of an eye on cosmic timescales. The fact that we see no evidence of this, no alien artifacts, no vast astro-engineering projects like Dyson spheres, and no visitors, suggests that something is profoundly wrong with our assumptions. The universe appears to be perfectly set up for life, yet it appears utterly empty of it beyond our own world. Scientists and thinkers have proposed a vast spectrum of potential solutions to this great silence, and each one challenges our worldview in a different way. One of the most unsettling ideas is the concept of the Great Filter. This theory, popularized by economist Robin Hanson, suggests that there is some kind of barrier, a critical evolutionary or technological step that is so improbable or so dangerous that it prevents almost all life from advancing to the point of interstellar communication or travel. The terrifying question for us is, where is this filter located? Is it behind us, perhaps the emergence of life itself, or the jump from simple prokaryotic cells to complex eukaryotic cells is astronomically rare? If so, we are incredibly lucky to have made it this far, and we might truly be alone. Or, even more chillingly, is the Great Filter still ahead of us? This is the more ominous possibility. It could be that the development of advanced technology inevitably leads to a civilization's destruction, perhaps through nuclear war, uncontrollable artificial intelligence, nanotechnology gone awry, or some other existential catastrophe we haven't even conceived of yet. In this view, the silence is a graveyard. Every civilization that reaches our level of technological maturity ultimately succumbs to its own creations, and the stars remain forever out of reach. Other explanations are less apocalyptic but no less mind-bending. Perhaps advanced civilizations are out there, but they are simply too alien for us to recognize. Their motives, their methods of communication, and their very existence might be so far beyond our comprehension that we are like ants at a picnic, completely unaware of the grand, complex events happening all around us. They might be using technologies based on principles of physics we have yet to discover, communicating through neutrinos or gravitational waves instead of radio. Or they might be deliberately avoiding us, following a kind of prime directive to not interfere with developing worlds like our own. Another possibility is that the galaxy is a dangerous place, and the smartest strategy for any long-lived civilization is to stay quiet, to hide from potential predators or rivals, making the universe seem empty by design. Each of these potential answers to the Fermi paradox forces a profound humility upon us. It defies our anthropocentric assumption that we are a standard model for intelligence and that others would develop technology and expand in ways we can easily recognize. The paradox holds up a mirror, making us question not just where the others are, but what the ultimate fate of a curious technological species really is. Are we poised on the brink of a great galactic community, or are we about to join the silent majority of civilizations that flashed into existence and then vanished without a trace? This line of thinking inevitably pushes the boundaries of speculation into the realm of the metaphysical, leading some to wonder if the answer lies not in astronomy or biology, but in the fundamental nature of reality itself. This line of inquiry, from the silence of the cosmos to the fine-tuning of its laws, inevitably forces us to question the very nature of reality. Are the physical constants a lucky roll of the dice, or do they hint at something even more extraordinary? This brings us to our seventh and perhaps most radical defiance of logic, the simulation hypothesis. The idea is as simple as it is profound. What if our universe, with all its galaxies, stars, and the rich tapestry of human history, is not base reality but an incredibly advanced simulation, a kind of cosmic video game running on the computer of a vastly more sophisticated civilization? This isn't just science fiction, it's a serious argument put forward by philosophers like Nick Bostrom. He suggests that if a civilization could ever reach a level of technological maturity where it could run vast, realistic simulations of conscious beings, and if such civilizations are common in the universe, then the number of simulated minds would vastly outnumber the number of biological, original minds. Statistically, therefore, the odds are that we are far more likely to be one of those simulations than we are to be the original, base reality creators. The hypothesis gains a startling amount of traction when we look at the very oddities of quantum mechanics we discussed earlier. Think about it. Why do particles jump between discrete energy levels instead of sliding smoothly? Why do they exist in a blur of probability until measured? This behavior is eerily reminiscent of how a computer program optimizes processing power. It only renders the details of a scene, the definite properties of a particle, when a player, an observer, is looking directly at it. It's a perfect way to save on computational resources. Furthermore, the universe itself appears to be pixelated at the smallest scale. Planck length and Planck time are thought to be the smallest possible units of space and time, the absolute resolution of reality. This looks less like a smooth, continuous cosmos and more like a digital grid, the underlying code of the simulation. Even the mathematical elegance of the laws of physics could be seen as programmed parameters, the elegant and efficient code written by the universe's developers. If this is true, it stands as the ultimate defiance of human logic. It means our deepest emotions, our sense of self, our entire history of struggle and triumph could be artificial constructs, lines of code in an unfathomably complex program. It completely upends our concepts of free will and purpose. Are our choices truly our own, or are they predetermined by the algorithms of the simulation? Does life have intrinsic meaning, or is it merely an elaborate entertainment for beings we can never comprehend? The very fact that the universe is comprehensible to us through mathematics and science could be seen as a clue. Perhaps we are discovering the rules of the program because we are, in some sense, part of the program itself, our innate curiosity, a feature deliberately built into our design. While entirely unprovable with our current understanding, the simulation hypothesis is a powerful thought experiment that reframes our entire existence. It challenges us to consider the ethics of our own actions. If we are in a simulation, would the creators judge us? If we one day create simulations of our own, populated with conscious artificial minds, what responsibilities would we have toward them? This digital perspective doesn't just live in the realm of philosophy. It finds a startling parallel in one of the most cutting-edge ideas in theoretical physics, a concept that suggests our three-dimensional reality might be nothing more than a projection on a distant, two-dimensional surface. If the simulation hypothesis makes you question the substance of reality, then our eighth unexpected defiance will make you question its very dimensions. This is the holographic principle, an idea so counterintuitive it seems ripped from the pages of science fiction. Yet it is a serious proposal from some of the world's leading theoretical physicists. The core concept is this: our rich, three-dimensional universe with its galaxies, planets, and the very space you feel around you might not be the fundamental reality. Instead, it could be a magnificent illusion, a holographic projection emanating from a two-dimensional surface that surrounds us at the unimaginably vast scale of the cosmic horizon. In this view, everything we see, touch, and experience is akin to a three-dimensional image encoded on a flat, two-dimensional plate, much like the security hologram on a credit card. The depth, the solidity, the very sense of distance, these are not primary qualities of the cosmos. They are emergent properties, a grand cosmic magic trick played on our senses. This astonishing idea didn't emerge from pure mathematical speculation. It was born from one of the most perplexing puzzles in modern physics, the black hole information paradox. When anything falls into a black hole, it vanishes behind the event horizon, the point of no return. According to the fundamental laws of quantum mechanics, information can never be truly destroyed. But according to general relativity, anything that crosses that horizon is lost forever to the universe. This created a deep conflict. The brilliant work of physicist Jacob Bekenstein and later Stephen Hawking showed that black holes are not completely black. They emit a faint radiation and slowly evaporate over astronomical timescales. This raised a terrifying question. When a black hole finally evaporates, what happens to all the information about the stars, planets, and atoms that fell into it? Is it truly lost, violating a cornerstone of quantum theory? Physicists Gerard T. Hooft and Leonard Susskind proposed a radical solution. They suggested that the information isn't lost inside the black hole at all. Instead, it is perfectly preserved, encoded on the surface of the event horizon itself. Every bit of data about what fell in is imprinted on this two-dimensional boundary. The three-dimensional interior is, in effect, a projection of that data. This resolution to a black hole puzzle had a universe-shattering implication. If the information for a three-dimensional region of space can be stored on its two-dimensional boundary for a black hole, perhaps this is a universal law. Perhaps the entire observable universe is itself a kind of black hole interior, and the distant cosmic horizon that marks the limit of what we can see is its two-dimensional boundary. All the information that makes up you, me, every galaxy, and every event in history could be encoded on that vast spherical shell. Our brains evolved to navigate a three-dimensional world, simply decode this information and interpret it as a world of volume and depth. This principle elegantly bridges the chasm between Einstein's theory of gravity, which describes the smooth geometry of space-time, and quantum mechanics, which describes the frantic dance of particles. In the holographic view, gravity in the three-dimensional bulk emerges from the quantum interactions happening on the two-dimensional boundary, offering a potential path to the long-sought theory of everything. The philosophical implications are staggering. It suggests that the universe is fundamentally about information. Reality is not made of tiny, solid billiard balls, but of bits, of yes/no answers to quantum questions. The solidity of the floor beneath your feet is a convincing illusion generated by your interaction with an inconceivably dense and complex flow of data. This challenges the most basic premise of our existence, that the world is real and continuous. If the holographic principle is true, then the universe is discrete and digital at its core, and our continuous experience of it is the ultimate virtual reality, far more sophisticated than any simulation we could ever conceive. It compels us to ask what is truly real. Is it the three-dimensional world we experience, or is it the two-dimensional source code from which it is projected? This perspective doesn't diminish the universe. It makes it even more marvelous, a cosmic artifact of unimaginable complexity where the boundaries of reality are not what they seem, leading us to consider an even broader canvas of existence where every possible reality might be playing out simultaneously. If the holographic principle makes our reality feel like a projection, then our ninth concept suggests the projector itself is just one in an infinite multiplex. This is the staggering idea of the multiverse, a theory that proposes our cosmos is not the entire story, but merely a single volume in a boundless library of realities, each with its own unique set of physical laws, constants, and histories. This isn't a fringe idea. It emerges naturally from two of our most successful scientific frameworks, inflationary cosmology and quantum mechanics. The theory of cosmic inflation suggests that the rapid expansion of space in the universe's first moments did not happen just once, but is an eternal process. In this view, our entire observable universe is just one bubble that inflated within a much vaster, possibly infinite, meta-universe. Elsewhere, other bubbles are constantly inflating into their own separate universes, each potentially with different fundamental properties. Quantum mechanics adds another layer to this proliferation of realities. The many-worlds interpretation proposed by Hugh Everett argues that every time a quantum event has multiple possible outcomes, the universe doesn't choose one. Instead, it splits, branching off into a new, parallel reality for each possibility. Every choice you've ever made, every random quantum fluctuation in a distant star, spawns new worlds where the alternative happened. This means that somewhere out there in the vast ensemble of universes, there is a reality where you never existed, another where the dinosaurs were never wiped out by an asteroid and still rule the Earth. Some where the Roman Empire never fell, and others where the laws of physics are so alien that matter as we know it cannot even form. Scientists like Max Tegmark and Andre Linde have developed detailed classifications for these multiverses, from Level 1 universes that are simply regions of space too distant for us to ever see, to Level 4 universes governed by completely different mathematical structures. This idea is a profound defiance of human logic because it radically recontextualizes our existence. It makes our universe seem incredibly insignificant, a single random sample plucked from an infinite array of possibilities. There is no grand design, no special reason our constants are fine-tuned for life. We simply find ourselves in one of the rare, habitable universes because we couldn't possibly observe one that isn't. This is the ultimate anthropic principle, explaining fine-tuning without any need for a creator or a deeper guiding hand. However, this elegant solution comes with a massive philosophical cost. It pushes the boundaries of science itself to the breaking point. If these other universes are forever beyond our cosmic horizon, separated from us by unimaginable distances or different dimensions, how can we ever find empirical evidence for them? The multiverse theory risks becoming untestable, moving from a scientific hypothesis into the realm of metaphysics. Some critics argue that if a theory predicts everything, then it effectively predicts nothing. How do we distinguish a good scientific theory from a bad one if all possible outcomes occur somewhere? Proponents counter that we might find indirect evidence, perhaps imprints left on the cosmic microwave background from collisions with other bubble universes in the distant past. Or we might discover a deeper theory that necessitates the existence of the multiverse, making its reality the most elegant and logical conclusion. This debate forces us to confront the very nature of science and what it means for something to be real if we can never interact with or observe it. Ultimately, the multiverse theory doesn't just explain the peculiarities of our universe. It connects to the most fundamental mystery of all, why there is something rather than nothing. If the multiverse is eternal and infinite, then the question of a first cause might be moot. There was never a true nothingness, just an endless sea of potential realities, with our universe being one inevitable fluctuation within it. This idea stretches our conception of existence to its absolute limit, suggesting that reality is not a single, neat, orderly system, but a chaotic, unending frenzy of creation where every possibility, no matter how bizarre, is realized somewhere. It is a humbling, awe-inspiring, and logically terrifying vision of a cosmos whose true scale and diversity are forever beyond our grasp, leaving us to wonder if every story we can imagine is, in some distant reality, actually true. From the mind-bending possibility of an infinite multiverse, we are drawn to perhaps the most fundamental and unsettling question of all, a mystery that has perplexed philosophers and physicists for centuries. This is the 10th, and in many ways the ultimate, way the universe defies human logic, the profound puzzle of why there is something rather than nothing. We intuitively believe that everything must have a cause. A chair exists because a carpenter built it. A storm occurs because of specific atmospheric conditions. This chain of cause and effect is the bedrock of our understanding. Yet, when we apply this same logic to the universe itself, we hit a wall of pure paradox. What caused the universe? What existed before the Big Bang? The most unsettling possibility is that the answer might be nothing. The universe in its entirety might be an uncaused, brute fact, a singular exception to the very rule of causality that it itself seems to enforce. This question was framed elegantly by the philosopher Gottfried Leibniz, who asked, "Why is there something rather than nothing?" He reasoned that for anything to exist, there must be a sufficient reason for its existence. Modern cosmology has attempted to provide a scientific answer, and the most compelling one involves the bizarre behavior of the quantum vacuum. We often think of a vacuum as pure, empty nothingness. But quantum physics reveals that what we call empty space is a seething, bubbling foam of potentiality. Virtual particles spontaneously pop into and out of existence, borrowing energy from the vacuum for an immeasurably brief moment before annihilating each other and returning it. This isn't just theoretical, it's a verified phenomenon with real-world effects, like the Casimir effect, where two metal plates placed extremely close together in a vacuum are pushed together by the pressure of these virtual particles fluctuating outside them. The prevailing theory is that our entire universe could be the result of one such quantum fluctuation on a cosmic scale, a random bubble of space-time that inflated into everything we see. In this view, the universe truly could have come from nothing, but this scientific answer, as elegant as it is, only pushes the mystery back one step. It doesn't actually explain the ultimate origin, it just changes the definition of nothing. Why do the laws of quantum physics exist? Why is there a quantum vacuum with these specific properties that allow for such fluctuations? Why is there a framework of physics at all that permits something to emerge from nothing? We are left with the same fundamental question, now dressed in the language of physics. We have simply replaced a universe from nothing with a set of physical laws from nothing. Some theories, like the cyclic model or the string theory landscape, attempt to address this by proposing an eternal, unending process. Perhaps our universe is just one in an infinite cycle of cosmic births and deaths, or one bubble in a forever inflating multiverse. But these models all assume some pre-existing framework, be it quantum fields, higher dimensional brains, or mathematical structures, that itself requires an explanation. They explain the how of our local universe, but not the ultimate why of existence itself. This leads us to a truly staggering possibility that defies all everyday logic. What if absolute nothingness, the complete and total absence of space, time, matter, energy, and physical law, is not a stable state? What if it is inherently unstable or even impossible? Philosopher Derek Parfit explored this idea, suggesting that the existence of nothing might be a far stranger and more illogical state than the existence of something. If that were true, then a universe is not a miraculous anomaly, it is an inevitability. Our very presence asking this question would be the cosmos's way of resolving a profound instability in the very concept of non-existence. This isn't a scientific answer, but a metaphysical one, highlighting the point where science, pressed to its absolute limit, begins to blend into philosophy. It forces us to confront the idea that our demand for a cause may be a limitation of our human minds, a cognitive bias evolved in a world of causes and effects, and not a rule that applies to the ultimate origin of reality itself. The universe might simply be, with no reason, no cause, and no explanation, a fact so basic and fundamental that it requires none, standing as the final, unanswerable defiance of our desire for a tidy, logical cosmos. This existential wonder at the sheer fact of existence seamlessly connects to another fundamental defiance, one that governs the very information we receive from the cosmos and challenges our perception of reality itself. Just when you think the universe has shown you its strangest face, it reveals a layer of reality so contradictory it feels like a cosmic joke. This is the 11th unexpected defiance, wave-particle duality. In our everyday world, we categorize things with absolute confidence. A sound is a wave vibrating through the air. A baseball is a particle, a solid object with a definite location. These categories are mutually exclusive, and our logic depends on them. But venture into the quantum realm, and this either-or thinking completely shatters. Light and matter do not abide by our human-made rules. Astonishingly, they behave as both waves and particles, and which nature they reveal depends entirely on how we choose to look at them. The most famous and elegant demonstration of this bizarre behavior is the double-slit experiment. Imagine a barrier with two thin, parallel slits cut into it. Behind it is a screen that records whatever hits it. Now fire a beam of particles, say electrons, at the barrier. If electrons were purely particles, as common sense would dictate, you would expect to see two distinct clusters on the screen behind the two slits, like someone spraying two streams of bullets. But that's not what happens. Instead, the screen shows a series of light and dark bands, an interference pattern. This is the unmistakable signature of a wave. It's the same pattern you get when water waves pass through two openings and ripple outward, with the peaks and troughs of the waves either reinforcing or cancelling each other out. The individual electrons seem to be going through both slits at once and interfering with themselves like a ghostly wave. Now, here is where the experiment twists into the truly unbelievable. What if you try to catch the electron in the act? You place a detector at one of the slits to determine which path each individual electron takes. The moment you do this, the magic vanishes. The interference pattern on the screen disappears. Instead, you get two simple bands, the pattern you would expect from plain, ordinary particles. The mere act of observing, of trying to pin down a definite path, forces the electron to abandon its wave-like behavior and act like a single, localized particle. It's as if the electron knows it's being watched and changes its behavior accordingly. This isn't a quirk of light or electrons alone. Molecules as large as buckaballs, soccer ball-shaped cages of carbon atoms, have been shown to produce these interference patterns. The universe is telling us that this duality is a fundamental feature of all matter. This profound paradox forced physicists to abandon the comfortable, deterministic clockwork universe of Isaac Newton and embrace the probabilistic, fuzzy world of quantum mechanics. The great Richard Feynman declared that the double-slit experiment contains the only mystery of quantum mechanics, the central weirdness from which all other quantum weirdness flows. The conclusion is as inescapable as it is strange. Particles do not have definite properties like position or momentum until they are measured. They exist in a nebulous cloud of potentialities, a superposition of all possible states. An electron is not a particle or a wave. It is something more fundamental that presents itself as one or the other depending on our interaction with it. This blurs the line between the object itself and the phenomenon of its measurement. There is no deeper reality hiding beneath. This is reality. This directly challenges the core of human intuition. We are wired to believe that objects have independent, definite identities. A chair is a chair whether you are looking at it or not, but quantum mechanics insists that at its most basic level, the universe does not work this way. Our classical world of solid objects and predictable paths is just a special case, an emergent property that arises from the frantic, ambiguous quantum activity happening underneath. It's like the clear, solid ice on a lake's surface. It seems definite and separate, but it's just a manifestation of the countless, jostling water molecules below. How do we make sense of a reality that is inherently ambiguous? We don't, in the classical sense. We instead develop a new intuition, one based on probability and potential. The wave-particle duality is intimately tied to another pillar of quantum weirdness, Werner Heisenberg's uncertainty principle, which states that there is a fundamental limit to how precisely we can know certain pairs of properties, like position and momentum. The more you try to pin down one, the more the other becomes fuzzy. This isn't a limitation of our instruments, it is a law of nature. The universe, it seems, is built not on certainty, but on a foundation of inherent uncertainty, a buzzing haze of possibility that only crystallizes into something definite through the act of observation. If the wave-particle duality showed us that reality is ambiguous, then the next principle solidifies that ambiguity as an ironclad law of the cosmos. This is the 12th unexpected defiance, the Heisenberg uncertainty principle. Formulated by the brilliant Werner Heisenberg in the late 1920s, this principle states a truth that is utterly counterintuitive. It is fundamentally impossible to know both the exact position and the exact momentum of a particle at the same time. The more precisely you measure one of these properties, the less precisely you can know the other. This is not a statement about the clumsiness of our instruments or the limits of our technology. It is a declaration about the very fabric of reality at the quantum scale. Uncertainty is not a bug in the system. It is a central, non-negotiable feature. To understand why this is so shocking, we have to step back into our classical, everyday worldview. Since the time of Newton, science operated on the dream of a clockwork universe, a perfect, deterministic cosmos where if you could know the exact position and velocity of every particle, you could calculate the entire future and rewind the entire past. It was a universe of absolute predictability. Heisenberg's principle shatters that dream completely. It tells us that the universe is inherently fuzzy at its core. This fuzziness arises from the wave-like nature of all matter. A particle isn't a tiny, solid marble with a well-defined location and speed. It is more accurately described as a wave packet, a blurry cloud of probability. To pinpoint its position very accurately, you have to squeeze this wave packet into a very narrow space. But a narrow wave packet is composed of a wide range of different momenta, meaning its velocity becomes highly uncertain. Conversely, a particle with a very precise momentum must be described by a long, smooth wave that is very spread out in space, making its position deeply vague. You cannot have both a sharply defined location and a sharply defined motion. The universe simply does not allow it. A common, though slightly misleading, explanation is that the act of measurement itself disturbs the system. For instance, to see an electron, you have to bounce a photon of light off of it. But that photon carries momentum, and when it hits the electron, it gives it a kick, changing its momentum in an unpredictable way. So, by measuring its position, you unavoidably alter its momentum. While this is a handy analogy, the deeper truth is even more radical. The uncertainty principle suggests that particles do not even possess exact, simultaneous values of position and momentum before they are measured. These properties are not pre-existing. They are conjured into a semi-definite state through the very act of observation. This moves us from a universe of certainty to a universe of probability, from a world of facts to a world of tendencies. This fundamental limit has profound practical and philosophical implications. On the practical side, it is the very engine of stability for our world. The uncertainty principle is why electrons don't simply spiral into the atomic nucleus. If an electron were ever to be confined to a single, precise point in the nucleus, its momentum, and therefore its energy, would become astronomically high, forcing it right back out. This quantum jitter keeps atoms stable, which in turn keeps you stable. It's also the bedrock of modern technologies like quantum cryptography. The security of these systems relies on the fact that any eavesdropper trying to measure a quantum key would inevitably disturb it, introducing uncertainties that alert the legitimate users to the presence of an intruder. Philosophically, the uncertainty principle forces a profound humility upon science and humanity. It places a hard limit on human knowledge. It tells us that there are aspects of reality that are, in principle, forever beyond our grasp. We can predict probabilities with stunning accuracy, but we can never predict individual events with absolute certainty. The universe is not a clockwork mechanism. It has an element of inherent randomness and unpredictability woven into its heart. This doesn't mean science is futile. It means that our knowledge of the world is necessarily statistical and probabilistic. We can know the universe deeply, but we can never know it perfectly. This inherent fuzziness at the quantum scale is a stark reminder that for all our power of observation, the cosmos retains fundamental mysteries, a theme that becomes overwhelmingly apparent when we look not at the tiny, but at the vast, mysterious dark components that make up most of everything. If the uncertainty principle revealed a fundamental fuzziness at the quantum scale, our next defiance exposes a far vaster and more profound ignorance, one that humbles every discovery that came before it. This is the 13th and perhaps most staggering way the universe defies our logic, the overwhelming dominance of dark matter and dark energy. For all our exploration and scientific triumph, we have been like children studying the foam on the crest of a wave, completely unaware of the immense, dark ocean beneath. Every star, every planet, every single thing you have ever seen or touched, all of it, every bit of so-called normal matter, accounts for a mere 5% of the universe. The remaining 95% is made of substances that are completely invisible to us, that do not interact with light, and that defy every conventional understanding of matter and energy. We are not just strangers in a strange land. We are barely a footnote in the cosmos's grand composition. The story of dark matter begins not in the vast emptiness between galaxies, but within them. In the 1930s, the brilliant astronomer Fritz Zwicky was studying the Coma Cluster, a massive group of galaxies. By measuring the velocities of the galaxies swirling around the cluster's center, he could calculate how much gravitational mass must be present to hold them all together. The result was shocking. The amount of mass required was hundreds of times greater than the mass of all the visible stars and gas combined. He called this missing mass Dunkle Materie, or dark matter. For decades, his work was largely ignored. Then, in the 1970s, Vera Rubin and her colleague Kent Ford performed a similar measurement, but this time within individual spiral galaxies. By carefully mapping the rotation curves, how fast stars orbit at different distances from a galaxy's center, they made a discovery that would revolutionize astronomy. According to Newton's laws, stars on the outer edges of a galaxy, far from the central bulge of mass, should orbit much more slowly, just as Pluto orbits the Sun more slowly than Earth. But Rubin found that these outer stars were whipping around just as fast as the inner ones. The only possible explanation was that each galaxy was embedded within an enormous, massive halo of some unseen material, a halo that provided the extra gravitational glue to prevent the galaxy from flying apart. This material, dark matter, does not emit, absorb, or reflect light. It simply is, interacting with the universe only through the force of gravity. While dark matter acts as the cosmic architect, sculpting the large-scale structure of the universe and holding it together, dark energy is the phantom force tearing it apart. Its discovery in the late 1990s was even more shocking. Two independent teams of astronomers were measuring the distances to far-off supernovae, expecting to find that the expansion of the universe was slowing down due to the gravitational pull of all matter. To their utter astonishment, they found the opposite. The expansion was accelerating. Something was actively pushing galaxies apart from one another at an ever-increasing rate. This something was dubbed dark energy. The leading theory is that it is a property of space itself, a repulsive force, a kind of anti-gravity encoded into the vacuum of empty space. The more the universe expands, the more space there is, and the stronger this repulsive force becomes, creating a runaway effect that will ultimately lead to a cold, dark, and isolated fate for all galaxies. This is the ultimate defiance. We are made of the rare, unusual stuff, the 5%. The cosmos is overwhelmingly composed of entities we cannot see, cannot touch, and do not understand. We only know they exist because of their gravitational effects on the tiny sliver of reality we can perceive. It's as if we've been trying to understand a grand opera by only studying the stage lights, completely deaf to the music and unaware of the vast theater. This forces a profound philosophical shift. Our perception of reality is not just limited, it is catastrophically incomplete. We have been building our models of physics on the exception, not the rule. The hunt to identify dark matter is one of the greatest scientific endeavors of our time, with experiments deep underground and in space trying to catch a fleeting glimpse of a hypothetical particle, like a WIMP, a weakly interacting massive particle. But so far, the silence is deafening. Dark energy is even more perplexing. Its nature is tied to the infamous cosmological constant problem and the vacuum energy of space, calculations for which are off by a staggering 120 orders of magnitude, the worst prediction in the history of science. This isn't a minor puzzle, it is a glaring sign that our most fundamental theories are missing something monumental. Why is the universe mostly hidden from us? This pervasive invisibility resonates with another profound information paradox, one that occurs at the boundary of the most destructive objects in the cosmos. If the overwhelming mystery of dark matter and dark energy shows us how little we know of the cosmos's contents, then the next defiance strikes at the very heart of our understanding of its fundamental laws. This is the 14th unexpected way the universe defies human logic, the black hole information paradox. It's a conflict so deep that it pits the two most successful theories in the history of physics, quantum mechanics and Einstein's general relativity, against each other, and in the process suggests that both might be profoundly incomplete. The core of the problem is a simple, devastating question. What happens to information when it falls into a black hole? In our daily lives, information seems intangible, but in physics, it is a concrete and sacred quantity. The fundamental tenet of quantum mechanics is that information can never be truly destroyed. It can be scrambled, it can be transformed, but it cannot be erased from the universe. If you burn a book, the ashes and smoke still contain, in principle, all the information needed to reconstruct every word. The arrangement of particles carries the story. Now take that same book and throw it into a black hole. According to Einstein's general relativity, the book will cross the event horizon, the point of no return, and be irretrievably lost. Its information is sealed inside, destined for the mysterious singularity at the center. This was puzzling enough, but the situation became infinitely worse with Stephen Hawking's revolutionary discovery in the 1970s. Hawking showed that black holes are not completely black. Due to bizarre quantum effects at the very edge of the event horizon, they slowly emit a faint glow of radiation, now known as Hawking radiation. This radiation causes the black hole to lose mass and, over astronomical timescales, completely evaporate. Here is the paradox in its most lethal form. The Hawking radiation that streams out into the universe as the black hole evaporates has been calculated to be completely random, featureless, and thermal. It is pure heat. It contains no information whatsoever about the specific book, or the star, or the hapless astronaut that fell in. Once the black hole is gone, all that remains is this random thermal radiation. The information about what created the black hole and what fell into it seems to have been utterly erased from existence. This violates the most bedrock principle of quantum mechanics, the law of unitarity, which is the guarantee that information is always preserved. We are left with a catastrophic choice. Either quantum mechanics is wrong and information can be destroyed, or general relativity is wrong, and our understanding of black holes is fundamentally flawed. Both options are unthinkable, as both theories have been verified with astonishing precision in their own domains. This paradox has spawned decades of fierce debate and some of the most daring ideas in modern physics. One of the most prominent solutions comes from the holographic principle, which we touched on earlier. It suggests that the information of everything that falls into the black hole is not actually lost inside. Instead, it is perfectly and completely encoded on the event horizon itself, the two-dimensional surface surrounding the black hole. The three-dimensional interior is a projection of that data. In this view, when Hawking radiation is emitted, it is not random. It is subtly imprinted with the information from this horizon, like a cosmic DVD player reading data off a disk. The information is never truly inside the black hole to be lost. It's always on the surface, and it is slowly and faithfully released back into the universe as the black hole evaporates. This is an elegant solution, but it requires a radical rethinking of locality, the idea that objects exist in a specific place. Another, more violent proposal is the firewall hypothesis. It suggests that to preserve information, the event horizon cannot be the smooth, uneventful space that general relativity predicts. Instead, it must be a searing wall of unimaginably high energy particles, a literal firewall that would instantly incinerate anything crossing it. This would prevent information from ever falling in to be lost in the first place, but it completely violates the principle of equivalence, a cornerstone of general relativity which states that an astronaut falling through the event horizon should feel no dramatic tearing apart forces. So, to save quantum mechanics, we might have to sacrifice a key part of Einstein's theory. This paradox defies logic because it reveals a schism in reality itself. The rules that govern the very large and the rules that govern the very small are at war with each other in the most extreme environment nature can provide. It forces us to ask what information really is. Is it a physical thing? Is space-time itself built out of bits of information? The resolution to the black hole information paradox likely requires a theory of quantum gravity, a way to merge general relativity and quantum mechanics into a single, coherent framework. Ideas like string theory and loop quantum gravity are attempts to build this bridge. This struggle implies that our familiar concepts of space and time are not fundamental. They might be emergent properties, a convenient illusion that arises from a deeper, more complex reality operating on a level we have not yet perceived. A reality where information is the true currency of the cosmos, and the fate of a book swallowed by a black hole is not an ending, but a transformation we are only beginning to understand. If the black hole information paradox reveals a war between our best theories, then the solution may require us to dismantle our most basic assumptions about the stage upon which the universe plays out. This brings us to our 15th and perhaps most foundational defiance of human logic, the concept of emergent space-time. We have always assumed that space and time are the fundamental, immutable backdrop of reality, the canvas upon which matter and energy are painted. But a growing chorus of physicists now proposes a far more radical idea, that space and time are not fundamental at all. They are illusions, emergent properties that arise from something deeper, more abstract, and completely foreign to our everyday experience. This idea draws powerful support from the way other familiar properties emerge in nature. Think about temperature. When you feel that a cup of coffee is hot, you are not sensing some fundamental essence of hotness. You are experiencing the macroscopic effect of countless molecules jiggling around at high speeds. Temperature doesn't exist for a single atom. It is a collective, statistical property that emerges from the frenetic dance of trillions of particles. In a very similar way, theorists like those working on loop quantum gravity or string theory suggest that the smooth, continuous spacetime described by Einstein is not the bottom level of reality. Instead, it emerges from a vast network of more basic entities. In loop quantum gravity, spacetime is proposed to be woven from discrete, finite loops, a kind of spin network, giving it a granular structure at the infinitesimally small Planck scale. In string theory, the familiar four dimensions of spacetime emerge from the vibrational dynamics of tiny, fundamental strings existing in a higher dimensional realm. The mechanism for this emergence appears to be deeply connected to a quantum phenomenon we've already explored, entanglement. Just as the mysterious connection between entangled particles seems to transcend space, it might also be the very glue that constructs space itself. Imagine two particles becoming entangled. Physicists like Mark van Romsdonk have proposed that this act of quantum connection actually stitches together the very space-time between them. The more quantum systems are entangled, the more complex and structured the emergent space-time becomes. In this view, the vast, three-dimensional volume we inhabit is a holographic projection of a vast web of quantum information and correlations stored on a two-dimensional surface. This means that the distance between two stars is not a primary, fundamental property. It is a derived concept, a measure of how much entanglement exists between the quantum information that makes up those stars. If you could somehow sever that entanglement, the space between them would literally cease to have the same meaning. The fabric of reality would unravel. The implications of this are staggering for our intuitive grasp of the cosmos. It explains why our theories of physics break down in the extreme conditions of a black hole singularity or at the moment of the Big Bang. It's not that the laws of physics fail, it's that space-time itself, as a useful concept, ceases to exist. In those regimes, the deeper, more fundamental reality of quantum relationships is laid bare, and our familiar notions of here and there, before and after, become meaningless. This perspective also offers a promising path to resolving the long-standing conflict between general relativity and quantum mechanics. By building space-time out of quantum bits, a theory of quantum gravity wouldn't have to force two incompatible systems to agree. It would simply show how one naturally gives rise to the other. This forces a profound philosophical shift. We must accept that the stage of reality is not permanent and fixed. The distance to the moon and the duration of your life are not absolute features of the universe. They are relative, constructed phenomena that depend on an underlying, invisible network of quantum connections. It means that at its heart, the universe might not be made of stuff in a place, but of relationships and information. This leads us to a final, haunting question that has puzzled philosophers and physicists for centuries. If reality is ultimately built from an abstract, mathematical network of information, why is the universe so perfectly and profoundly describable by mathematics in the first place? This uncanny partnership between abstract thought and physical reality brings us to our 16th and perhaps most intellectually humbling defiance: the unreasonable effectiveness of mathematics. It is a profound puzzle that the universe, in all its complex and chaotic glory, can be so perfectly described and predicted by a language of symbols and equations that we invented inside our own minds. From the elegant dance of planets governed by Newton's calculus to the bizarre probabilities of quantum mechanics and the mind-bending curvature of space-time in Einstein's equations, mathematics provides an unnervingly precise map of reality. It feels less like we are creating tools to measure the world and more like we are uncovering a secret code that the cosmos was built upon, a pre-existing operating system written in numbers. The physicist Eugene Wigner famously wrestled with this, marveling that this mathematical power is a gift we neither deserve nor fully understand, a mystery that borders on the miraculous. Consider the breathtaking predictive power of pure math. Paul Dirac wasn't tinkering in a lab when he discovered antimatter. He was staring at an equation. His work to make quantum mechanics consistent with Einstein's special relativity resulted in a beautiful but puzzling formula. This equation had two solutions, one for the electron and one for a particle with the same mass but opposite charge, a concept utterly unknown to science at the time. Rather than dismiss it as a mathematical artifact, Dirac trusted the numbers. His faith was rewarded just a few years later with the experimental discovery of the positron, the electron's antimatter twin. The math had seen a fundamental truth of reality years before our instruments could confirm it. This pattern repeats throughout history. The complex numbers once dismissed as imaginary are now the essential language of quantum physics and electrical engineering. The non-Euclidean geometries developed as abstract intellectual exercises became the necessary framework for describing the warped geometry of the cosmos in general relativity. It's as if every time a mathematician follows a thread of pure logic for its own aesthetic sake, a physicist later finds that thread woven into the very fabric of the universe. This incredible synergy forces a deep philosophical question that has divided thinkers for centuries. Is mathematics discovered or invented? The Platonist view argues that mathematical truths exist in an abstract, eternal realm independent of humanity. A physicist like Roger Penrose might say that a mathematician is an explorer, uncovering pre-existing truths like a mountaineer summiting a peak that was always there. The number pi, the ratio of a circle's circumference to its diameter, would be true in any universe for any intelligent species. It is a discovery. The opposing view argues that math is a human invention, a particularly useful language and set of logical rules we have developed to organize our sensory experiences. In this view, we tune our mathematics to fit what we observe. We didn't find the law of gravity written on a rock. We constructed a model, F equals g times m1 m2 over r squared, that perfectly describes how objects attract one another. Yet, the unreasonable effectiveness of math suggests that even if it is an invention, its power is far greater than it should be. Our invented models don't just describe what we've already seen, they accurately predict phenomena we've never imagined in realms far beyond human scale. This hints at a breathtakingly deep connection between the human mind and the cosmos. It implies that the logical structures our brains are capable of constructing are somehow resonant with the logical structures that underpin physical reality. Our consciousness may not be a passive observer of the universe, but an active participant in a reality that is, at its heart, fundamentally mathematical. This interplay suggests that the ultimate laws of nature are not written in a language of force or substance, but in the timeless, ethereal language of mathematics, a code that we are only just beginning to crack. This profound intelligibility of the cosmos through numbers makes the next great defiance all the more striking, for it concerns a fundamental aspect of reality that remains stubbornly unintelligible and deeply asymmetric: the relentless and mysterious arrow of time. This relentless, one-way flow of time is perhaps the most intimate and inescapable way the universe defies our logic. We all feel it, this irreversible march from a fixed past into an uncertain future. It seems so obvious, so fundamental to existence itself, yet when we turn to the fundamental laws of physics, this arrow of time completely vanishes. The equations that govern the universe, from Newton's mechanics to Einstein's relativity to quantum electrodynamics, are almost entirely time-symmetric. They work perfectly whether time is running forward or backward. If you were to watch a film of two planets orbiting each other or two electrons colliding and scattering, you would be utterly unable to tell if the film was being played forward or in reverse. Both sequences would obey the laws of physics perfectly. At the most fundamental level, the universe does not seem to care which way time flows, so why do we experience it so powerfully as a one-way street? The key that unlocks this paradox is a concept that feels much more mundane but is in fact profoundly deep: disorder. This is the domain of the second law of thermodynamics, which states that the total entropy or disorder of an isolated system always increases over time. It's the reason a drop of ink diffuses in a glass of water but never spontaneously reassembles itself into a neat drop. It's why a shattered cup does not leap off the floor and reassemble on the table. The universe as a whole is moving from a state of lower entropy to a state of higher entropy, from order to disorder. This ever-increasing disorder provides the arrow we experience. It gives us a powerful, objective way to distinguish the past from the future. The past is the state of lower entropy. The future is the state of higher entropy. Our memories rely on this principle. To form a memory, your brain must undergo a physical change, a process that increases entropy in your surroundings. That's why we remember the past, the low entropy state, and not the future. But this only pushes the mystery one step further. Why was the entropy of the early universe so astonishingly low? This is the true heart of the puzzle, as physicists like Sean Carroll have eloquently explored. The Big Bang did not start in a state of maximum disorder or thermal equilibrium, which would be the most statistically likely and generic state. Instead, it began in a condition of exquisitely low entropy, an incredibly hot, dense, and remarkably smooth state. This was the ultimate wound-up clock, set to unwind for billions of years. All the increase in entropy we see around us, stars burning out, galaxies dispersing, our own lives progressing from order to disorder, is just the universe playing out the consequences of that very special, very unlikely initial condition. We are living in the aftermath of that moment, riding the wave of increasing entropy that defines our experience of time. And this leaves us with the deepest, most logical defiance of all. Why? Why did the universe begin in such a fantastically specific and improbable configuration? This is not answered by our current physics, it is assumed by it. Some theories point to the multiverse, suggesting that our universe is just one bubble in a vast foam, and we simply find ourselves in one of the rare bubbles that started with low entropy, allowing for the complexity and life that can ask such questions. Others, like the ideas of Roger Penrose, propose a cyclical model where the end of one universe somehow gives rise to the low entropy beginning of the next. But the fundamental riddle remains. The arrow of time is not written into the laws of physics themselves, but is instead a ghostly emergent property, a story written by the universe's initial conditions. It is a story we are intimately a part of, for our very consciousness seems to be tied to this processing of information from order to disorder, from a definite past to a probabilistic future. This profound connection between the cosmic and the conscious makes the next great defiance feel not like an abstract puzzle, but a deeply personal one. Just as the arrow of time forces us to confront the universe's initial conditions, we now turn inward to a mystery that is not out among the stars, but is the very medium through which we perceive those stars at all. This is the 18th unexpected defiance, the hard problem of consciousness. It is the profound struggle to understand how and why the intricate firing of neurons and the chemical exchanges in a lump of gray matter, a physical object made of the same atoms as a rock or a star, give rise to the rich inner world of subjective experience. Why does the processing of light of a specific wavelength by our visual cortex produce the subjective, internal sensation of the color red? Why does the complex neural network we call a brain not merely process information like a sophisticated computer, but also feel? It feels like something to be you, to be happy, to taste chocolate, or to stare in awe at a sunset. This what it is like-ness is the central mystery, and it stands as a glaring exception to the reductionist dream that everything can be explained by breaking it down into its physical parts. The term was coined by philosopher David Chalmers to draw a crucial distinction. He separated the so-called easy problems of consciousness, which are still monumentally difficult but tractable with standard scientific methods, from the truly hard problem. The easy problems involve explaining the functions and mechanics of the brain, how we focus our attention, how we integrate sensory information, how we report on our internal states. We are making incredible progress on these fronts with brain scans and cognitive models, but the hard problem is different. It asks why performing these functions is accompanied by subjective experience at all. Even if we could perfectly map every neural correlate of consciousness, every single synapse that fires when you see the color blue, we would still be left with a colossal why. Why does that particular pattern of electrical activity generate the experience of blueness? It's the difference between understanding the hardware and software of a computer and wondering if it feels bored while running a spreadsheet calculation. This logical defiance suggests a possibility that makes many scientists deeply uncomfortable. That consciousness might not be something that emerges from complex computation. Instead, it might be a fundamental feature of the universe, as basic and irreducible as space, time, and mass. This view, often called panpsychism, doesn't mean that rocks are conscious in the way we are. But it does propose that the fundamental constituents of reality, perhaps electrons and quarks, possess some tiny, primitive form of experience or proto-consciousness. In this view, the human mind is not a generator of consciousness but a complex receiver or organizer of it. Much like a television doesn't generate the electromagnetic signals but organizes them into a coherent picture. The brain might be less like an engine creating steam and more like a tuning dial focusing a radio wave that is already everywhere. This idea, while seemingly wild, offers a potential bridge across the explanatory gap between the objective physical world and our subjective inner lives, a gap that conventional materialist science has found utterly impassable. This mystery resonates powerfully with the fine-tuning problem we encountered earlier. The universe's laws appear perfectly calibrated not just for the existence of stars and planets, but for the eventual emergence of beings who can look back at the cosmos and wonder about it. It feels as if consciousness is not a random, accidental byproduct, but is somehow written into the cosmic blueprint from the very beginning. This leads to a breathtaking, almost mystical consideration. If consciousness is fundamental and the universe has all the necessary ingredients, could the cosmos itself be aware? This is not necessarily a claim about a personal, thinking God, but rather a speculation that the universe might possess a holistic, low-grade form of awareness, a cosmic consciousness of which our individual minds are merely isolated fragments. The hard problem of consciousness ultimately defies our logic because it places the observer, the very thing doing the science, at the center of the greatest scientific puzzle of all. It forces us to consider that the tools of physics and chemistry, designed to measure an objective external world, might be fundamentally unequipped to explain the subjective internal world that is doing the measuring, suggesting that a complete theory of reality may require us to finally develop a science of the subjective. This circular but profound reasoning, known as the Anthropic Principle, forces us to confront a selection bias so fundamental it can feel like a philosophical trap. The universe's physical constants and laws appear exquisitely fine-tuned for life, but perhaps that's only because we are here to observe them. If the cosmos were any different, if gravity were a fraction stronger or the cosmological constant a hair larger, then no planets would form, no stars would shine, and no conscious beings would ever arise to wonder about the apparent perfection. Our very existence acts as a filter, ensuring that any universe we can possibly find ourselves in will, by necessity, have the right conditions for us. This turns the staggering improbability of fine-tuning from a miraculous coincidence into a simple, almost trivial, statistical inevitability. We are not seeing a universe designed for life. We are life that has emerged in a universe that allows it, and our observation is limited to that single, fortunate data point. The principle is often discussed in two distinct forms, each with its own staggering implications. The weak anthropic principle is the more conservative scientific stance. It simply states that we must be prepared to account for the fact that our location in the universe is necessarily privileged to the extent of being compatible with our existence as observers. It's a cautionary note for cosmologists. When you calculate the probability of our universe, remember that you are a living entity who can only perform that calculation in a universe that permits life. It doesn't explain why such a universe exists. It just notes that we couldn't be anywhere else. The strong anthropic principle, however, takes a far more radical leap. It proposes that the universe must have those properties that allow life to develop at some stage in its history. This version suggests that the emergence of consciousness is not a lucky accident but a fundamental feature of the cosmos, as if the universe had a built-in bias or even a compulsion to eventually produce observers. This stronger view inevitably veers into metaphysical territory, hinting at a teleological or purpose-driven framework for reality, or powerfully supporting the multiverse theory as the only way to make sense of such a profound bias. This line of thinking defies our standard logic because it feels like a tautology, a circular argument that uses our existence as proof of the conditions that led to our existence. And yet, within the vastness of cosmology and probability, it is a perfectly valid, albeit humbling, statistical point. It forces a kind of cosmic Copernican principle on us, not about our physical place in the universe, but about our status as observers. We are not special, we are inevitable, but only in the specific kind of universe that can produce us. This reasoning connects directly to one of the most bizarre and unsettling thought experiments in all of physics, the concept of Boltzmann brains. Named for the 19th century physicist Ludwig Boltzmann, who pondered the statistical nature of entropy, the idea proposes that in a vast, eternally existing universe trending toward maximum disorder, random fluctuations could occasionally and inevitably create order out of chaos. Given enough time, a fully formed, self-aware brain could spontaneously assemble from the void, complete with a lifetime of false memories and a complete sensory illusion of a consistent reality, only to almost instantly dissolve back into the chaos. If such disembodied observers are statistically more likely to randomly fluctuate into existence than a vast, ordered, 13.8 billion-year-old cosmos with billions of conscious beings, then how can we ourselves be sure that we are not merely fleeting Boltzmann brains, hallucinating a universe that doesn't truly exist? The anthropic principle, intended to ground us, ultimately pulls the rug out from under our certainty, making us question the very reliability of our observations and memories, and pushing us to wonder if our entire experienced reality is nothing more than a fleeting statistical glitch in an otherwise mindless void. If the anthropic principle left us questioning our cosmic significance, then prepare for a thought experiment that attacks the very foundation of reality as you know it. This is the 20th unexpected defiance, and it is perhaps the most existentially terrifying of them all, the paradox of Boltzmann brains. It's an idea so unsettling that most physicists consider it a reductio ad absurdum. A logical argument that proves its own premises must be false by leading to an insane conclusion. The premise is rooted in the second law of thermodynamics and the statistical nature of entropy. In an infinitely old and vast universe, or one that persists for an unimaginably long time toward a state of maximum disorder, random fluctuations become not just possible but inevitable. Given enough time, the atoms in a void will eventually, through sheer chance, arrange themselves into any configuration, no matter how complex. This includes the spontaneous, random formation of a fully functioning, self-aware human brain, complete with a complete set of fabricated memories and a perfect sensory illusion of an entire universe, all in the emptiness of space. This phantom observer would believe it is a person living on a planet with a past and a future, only to almost instantly dissolve back into the chaotic vacuum from which it came. This nightmare scenario is named for the physicist Ludwig Boltzmann, who in the late 19th century used statistical fluctuations to explain how pockets of order could appear in a universe tending toward disorder. The terrifying logical extension is this: if the universe is eternal and random, then the spontaneous, random fluctuation of a single, isolated brain is astronomically more probable than the gradual, painstaking evolution of an entire ordered cosmos spanning billions of light years and billions of years. It is far easier for the universe to randomly assemble one self-aware mind for a single second than it is to assemble trillions of galaxies, stars, planets, and a continuous history. Therefore, if these are the rules, the statistical odds suggest that entities like us who believe we are the products of a long, ordered cosmic evolution should be overwhelmingly outnumbered by these disembodied, fleeting Boltzmann brains popping in and out of existence. The conclusion is inescapable and horrifying. You are far more likely to be one of these momentary illusions than a genuine product of a 13.8 billion-year-old universe. Your memories of watching this video, your sense of self, your entire life history, all of it could be nothing more than a fantastically detailed and utterly false hallucination, a cosmic accident with no connection to any external reality. Unsurprisingly, the scientific community largely rejects this conclusion, not because it's frightening, but because it is scientifically useless. If we cannot trust that our memories and observations reflect a real, consistent past, then the entire foundation of science, from geology and evolutionary biology to cosmology itself, crumbles into dust. We can't prove the Big Bang happened if our memory of the evidence for it might have formed a split second ago. The paradox is therefore seen as a powerful sign that our underlying assumptions are wrong. The prevailing theory of cosmic inflation provides the most popular escape route. It suggests our universe is not an eternal, static arena, but had a definite beginning in the Big Bang, and that its early state of incredibly low entropy was not a random fluctuation but a product of the laws of physics. In this view, the conditions for genuine, evolved observers like us are not impossibly rare, but are a natural outcome of the universe's birth and expansion. The Boltzmann brain paradox thus serves a vital purpose. It acts as a boundary, a sanity check for our cosmological models. Any theory that makes the existence of Boltzmann brains more likely than that of ordinary observers is considered a theory in serious need of revision. This descent into a reality where observation and illusion become indistinguishable brings us full circle, connecting back to the very first quantum mysteries we explored. The question of how we can trust our perceptions if we might be Boltzmann brains finds a disturbing parallel in the quantum realm, where the very act of observation seems to define reality. This uncertainty is the core of one of the most enduring enigmas in all of physics, a problem that has divided interpretations for a century and forces us to ask what really happens during the act of measurement. This descent into a reality where observation and illusion become indistinguishable brings us full circle, connecting back to the very first quantum mysteries we explored. The question of how we can trust our perceptions if we might be Boltzmann brains finds a disturbing parallel in the quantum realm, where the very act of observation seems to define reality. This uncertainty is the core of one of the most enduring enigmas in all of physics, a problem that has divided interpretations for a century and forces us to ask what really happens during the act of measurement. We find ourselves at the 21st unexpected defiance, the quantum measurement problem. This is the deep, unresolved chasm at the very heart of quantum mechanics. We've seen how particles exist in a ghostly superposition of states, a blur of probabilities described by a wave function. The mathematics is crystal clear on how this wave evolves. It follows the smooth, deterministic path of the Schrödinger equation. But then, the moment we make a measurement, this elegant, continuous evolution shatters. The wave function collapses, the myriad possibilities vanish, and a single, definite outcome clicks into place on our detector. The electron, which was a cloud of here and there, is now definitively here. The monumental, logic-defying question is, what exactly constitutes a measurement? What is the precise physical mechanism that triggers this sudden, irreversible collapse? The standard interpretation, the Copenhagen interpretation championed by Niels Bohr and Werner Heisenberg, offers a stark answer with profound implications. It states that the wave function collapse is not a physical process but an epistemological one, an update in our knowledge. There is no deeper reality. The particle doesn't have a definite position until the act of measurement forces it to choose. But this raises the terrifying specter of consciousness. If a measurement is just a physical interaction, a photon hitting an electron, then that photon itself should become entangled with the electron, becoming part of a larger, still uncertain quantum system. This chain of interactions would continue from the detector to the computer screen to the light entering your eye. By this logic, the entire universe should be in one gargantuan superposition. The Copenhagen interpretation cuts this chain with a seemingly arbitrary knife. Collapse happens at the point of a conscious observation. This places human consciousness, or any form of awareness, in a bizarrely privileged position in the universe, seemingly acting back upon the physical world to crystallize it into reality. This is a notion that many physicists find deeply unsatisfactory, as it introduces a mystical element into the clean, mathematical framework of physics. In direct opposition to this stands the many worlds interpretation proposed by Hugh Everett. It takes the mathematics of quantum mechanics at its absolute face value. Everett argued that the Schrödinger equation always holds true. The wave function never collapses. So what happens during a measurement? The universe literally splits. Every single possible outcome of a quantum event actually occurs, but each one plays out in a newly branched parallel reality. In one world, you see the electron on the left. In another, an identical version of you sees it on the right. There is no collapse and consciousness has no special role. The appeal is its elegant purity. It removes the arbitrary measurement postulate. But the cost is an infinitely proliferating multiverse of near-identical copies, and it leaves us with a new, equally baffling question. If every possibility happens, why do we, in this particular branch, experience only one specific, seemingly random outcome? The theory explains everything that can happen, but it cannot explain why we experience what we do. It defies our logic by making our individual experience feel insignificant, a single thread in an infinite tapestry of possibilities. Other interpretations abound, each trying to solve the riddle. The de Broglie-Bohm pilot wave theory suggests particles are real and have definite positions at all times, guided by a mysterious pilot wave that ensures they statistically match quantum predictions. The objective collapse models propose that wave function collapse is a real physical process, triggered not by consciousness but by a threshold of complexity or a fundamental randomness in space-time itself. Yet, after nearly a century of debate, no consensus has been reached. The measurement problem persists because it strikes at the very nature of reality, asking us whether our observations create the world or merely discover it. This profound ambiguity, this lack of a solid ground upon which to build a description of reality, finds a strange and beautiful echo in Einstein's theory of relativity, which dismantles another one of our most basic assumptions, that there is a single, universal perspective from which to view the cosmos. Just when you think the universe has challenged every assumption about the self and the act of observation, it delivers a blow to one of our most deeply held collective beliefs, the idea that we all share the same present moment. This is the 22nd unexpected defiance, the relativity of simultaneity. In our daily lives, we operate under the unshakable conviction that if two events happen at the same time, they are simultaneous for everyone, everywhere. A lightning bolt striking a tree and another striking a mountain peak a mile away occur at the same instant, and we assume any observer would agree. This universal now feels like the most objective fact of existence. But Einstein's special relativity reveals this to be a profound illusion, a parochial viewpoint limited by our slow speeds. Simultaneity is not absolute, it is relative to your state of motion. To grasp why this must be true, we have to return to one of the pillars of Einstein's theory, the absolute, unchanging speed of light. Imagine a thought experiment central to his revelation. A person is standing on a railway platform, exactly midway between two poles. At the precise moment they are in the middle, two bolts of lightning strike the poles simultaneously. Because the light from each strike has an equal distance to travel, it reaches the observer's eyes at the same instant. For them, the events are unquestionably simultaneous. Now picture a second observer sitting on a train speeding past the platform at a significant fraction of the speed of light. At the exact instant the lightning strikes, from the platform observer's perspective, this moving observer is also perfectly positioned exactly midway between the two poles. But here's the catch: the train is moving. By the time the light flashes travel from the poles toward the observer, the train has moved forward. This means the light from the strike at the pole behind the train has a shorter distance to travel to catch up to the moving observer, while the light from the strike ahead of the train has a slightly longer distance to cover. Consequently, the observer on the train will see the lightning strike the rear pole first and the forward pole a moment later. For them, the two events were not simultaneous. Crucially, this is not an illusion of perception. It is a statement about reality itself. There is no privileged perspective. Both observers are equally correct. The very ordering of events in time depends on how you are moving. This has staggering implications that ripple out from the philosophical to the intensely practical. Our entire global infrastructure relies on the fact that we must account for this relativity every single second. The atomic clocks on GPS satellites orbit the Earth at about 14,000 kilometers per hour. According to special relativity, because they are moving so fast relative to us on the ground, their clocks should run slower, falling behind by about 7 microseconds per day. But they are also higher in Earth's gravitational well, and general relativity tells us that in weaker gravity, clocks run faster, speeding them up by about 45 microseconds per day. The net effect is that the satellite's clocks gain about 38 microseconds each day relative to clocks on the surface. If the engineers who designed the GPS system did not deliberately correct for these competing relativistic effects, these distortions of time and simultaneity, the entire network would become useless within minutes. The navigation data would be off by over 6 miles per day, making turn-by-turn directions completely incoherent. Your ability to find a coffee shop is a silent, constant testament to the fact that there is no universal clock ticking for us all. Philosophically, this shatters the Newtonian concept of a single, flowing river of time that everyone shares. It dismantles the idea of a cosmic now that sweeps across the universe. Your present moment and my present moment are not the same if we are moving relative to each other. This forces us to confront the block universe theory we explored earlier, where the past, present, and future all equally exist in a four-dimensional spacetime. In this view, the relativity of simultaneity is not a bug but a feature. It shows that now is a local, personal concept, not a global one. This has profound consequences for our understanding of causality, the sacred rule that cause must precede effect. For causality to be protected, for the logical flow of the universe to be maintained, no observer, regardless of their motion, can ever see an effect happen before its cause. The laws of physics ensure this by preventing any signal or influence from traveling faster than light. But for events that are separated in space and are not causally connected, the order in which they occur can be genuinely ambiguous, depending entirely on your frame of reference. This suggests that reality is not a sequence of events but a vast, fixed structure of events, and our journey through it, feeling the passage of time, is what creates our personal, unique story within the grand, static tapestry of space-time. This profound interweaving of time, space, and perspective makes the final, ultimate defiance of human logic all the more powerful, for it asks why this vast, relativistic, seemingly arbitrary cosmos is governed by any laws at all. After the dizzying implications of relative time and subjective now, we arrive at a question so profound it has puzzled philosophers and physicists for millennia, a mystery that lies at the absolute bedrock of reality itself. This is the 23rd unexpected defiance, the inexplicable origin of the physical laws. We spend our lives discovering and utilizing these laws. Gravity tells an apple how to fall. Electromagnetism tells light how to shine. We have codified them into elegant mathematical equations that predict the cosmos's behavior with breathtaking accuracy. But we never stop to ask the most logical and ultimately unanswerable question: why are these laws what they are? Why does F equal ma? Why is the gravitational constant the precise value it is, and not a number slightly larger or smaller? The universe doesn't have to be orderly. It doesn't have to be comprehensible. It could be pure, random chaos. The fact that it isn't, the fact that it operates according to consistent mathematical rules, is the greatest unsolved puzzle in all of science. This inquiry inevitably pushes beyond the boundaries of physics and into the realms of philosophy and theology. Scientists like Stephen Hawking and Leonard Mlodinow wrestled with this in their work, pondering whether these laws are unique to our universe or if they are merely local bylaws in a vast multiverse. In that view, our universe is just one bubble in a frothing cosmic foam, each bubble with its own random, unique set of physical constants and laws. We, of course, find ourselves in one of the rare bubbles where the laws are conducive to the formation of galaxies, stars, planets, and life. This anthropic reasoning explains the apparent fine-tuning without needing a deeper reason, but this answer, while elegant, feels deeply unsatisfying. It doesn't explain why there is a framework that allows for different laws at all. It simply shifts the question back a step. Why is there a meta-law that governs the multiverse and allows for this variation? We are left with an infinite regression, a chain of why questions that never seems to bottom out. This is the ultimate defiance of our logic. As humans, we are explanation engines. We are wired to believe that everything has a cause, a reason, a mechanism. But when we drill down to the fundamental laws of physics, we hit a wall of pure brute fact. The laws simply are. They exist without a reason. The philosopher Ludwig Wittgenstein captured this frustrating limit when he stated, "The existence of the natural law cannot be described, it can only be shown." We can describe how gravity behaves, but we cannot explain why the law of gravity exists. Some theories suggest that these laws are not fundamental but emergent. Perhaps they arise from something deeper, like the symmetries of empty space or the complex interactions of an underlying network of information. Just as the law of temperature emerges from the jiggling of atoms, a concept that has no meaning for a single particle, perhaps the great laws of the cosmos emerge from a more basic and currently invisible level of reality. This possibility implies a universe that is fundamentally rational and ordered, yet whose deepest order may be forever inexplicable, not because of our ignorance, but because explanation itself may require a framework that ceases to exist at that most basic level. We are left with a sense of awe at the sheer existence of this cosmic order. Why is there a magnificent mathematical symphony instead of meaningless noise? This mystery is the silent foundation upon which all other mysteries are built. It suggests that the universe is, at its heart, a system of immense and profound rationality, a system that seems to be not only written in the language of mathematics, but one that appears to be running a computation. This inescapable feeling that the cosmos is not just described by math, but is actively calculating something, leads us directly to our next and penultimate defiance: the idea that the universe itself might be one gargantuan, unimaginably complex computer. If the fundamental laws of the universe feel like an unbreakable code, then perhaps that's exactly what they are. This brings us to our 24th unexpected defiance, a concept that reframes the entire cosmos not as a collection of things, but as a vast, ongoing process of calculation. This is the idea of the universe as a computer, a perspective known as digital physics or the computational universe hypothesis. In this view, the bedrock of reality isn't matter or energy, but information. Every particle interaction, every force, every event in the cosmos is akin to a digital computation. The universe isn't just described by mathematics. It might literally be running a mathematical algorithm. This radical idea has deep roots. In the 1960s, German engineer and computer pioneer Konrad Zuse proposed that the cosmos was a giant digital computer. Later, physicist Edward Fredkin developed this into a full-fledged philosophy, suggesting the universe is fundamentally discrete and finite, composed of a finite number of tiny space-time cells, much like the pixels on a screen. In Fredkin's view, reality isn't smooth and continuous. It's pixelated at the Planck scale, and the evolution of these pixels over time is governed by a set of computational rules, a cosmic software program. The laws of physics, then, are not mysterious, eternal equations. They are the emergent properties of this underlying digital computation, just as the complex behavior of a video game emerges from the binary logic of its code. This perspective offers a stunningly elegant explanation for some of the quantum weirdness we've already explored. Why do particles exhibit wave-particle duality and exist in superpositions? Perhaps because the universe's processor is rendering probabilities before collapsing them into a definite state upon observation. Why is there a fundamental limit to knowledge, as expressed in the Heisenberg uncertainty principle? It could be a reflection of the finite resolution of the cosmic grid, a fundamental pixel size for reality. The holographic principle, where a three-dimensional universe is encoded on a two-dimensional surface, fits perfectly within this framework. It's a data compression scheme of unimaginable sophistication. Even the arrow of time could be seen as the irreversible processing of this cosmic computation, moving from one state to the next in a sequence that cannot be reversed. The implications are as profound as they are disorienting. It suggests that you, me, the stars, and the void between them are not made of solid stuff, but are incredibly complex patterns of information. We are not physical beings having an experience. We are informational processes being run on the hardware of the universe. This raises existential questions that defy our classical logic. If the universe is a computation, who or what is the programmer? Is it a being in a higher reality, or could the laws of mathematics and logic themselves be a sufficient cause, a self-contained program that simply booted up? And what is the purpose of the calculation? Is the universe simply calculating itself into existence, with consciousness being a particularly complex subroutine that has become aware of its own code? This viewpoint doesn't necessarily make life meaningless. Instead, it transposes meaning into a different key. Our purpose might be to understand the program, to experience its output, or perhaps to contribute our own unique data to the ongoing computation. This computational view of everything leads us directly to the final, and perhaps most beautiful, defiance of human logic. It's a mystery that has been pondered by everyone from Albert Einstein to Eugene Wigner, a puzzle so deep it underlies every single discovery we've discussed. Why is any of this comprehensible to us at all? Stand in awe for a moment, not at the vastness of the cosmos, but at a miracle happening right inside your own mind. After a journey through quantum spookiness, elastic time, and silent alien graveyards, we arrive at the final, and perhaps most profound, defiance of all. The simple, staggering fact that you can understand any of this. The universe is comprehensible. This is not a small thing. We are a species of recently evolved apes on a tiny, wet rock orbiting an average star in a quiet suburb of a galaxy. And yet we have managed to decipher the laws that govern the birth of stars, the fabric of space-time, and the behavior of particles so small they barely seem to exist. We have not just observed these things, we have understood them. We have translated the cosmos into a language of mathematics that we invented inside our own heads. As Albert Einstein himself marveled, the most incomprehensible thing about the universe is that it is comprehensible. Why should this be? There is no logical, inevitable reason why the cosmos should be intelligible to us. The universe could easily be a place of pure, arbitrary chaos, where causes and effects are disconnected and no consistent rules apply. Or its laws could be so alien, so deeply hidden, or so complex that they forever exceed the grasp of our 3-pound brains, which evolved to spot predators on the savannah, not to contemplate the geometry of 11-dimensional superstrings. The fact that we can point our telescopes to the heavens, run experiments in particle colliders, and find that the results not only make sense but are predictable and repeatable is a breathtaking cosmic coincidence. It suggests a deep, pre-established harmony between the human mind and the universe's underlying structure, a resonance that allows us to tune into the fundamental frequency of reality. Philosophers have wrestled with this mystery for centuries. Immanuel Kant argued that we can never know the true thing in itself, the universe as it truly is. Instead, he proposed, our minds impose categories like space, time, and causality onto our sensory input, creating a picture of reality that is orderly precisely because our brains are built to make it orderly. In this view, the comprehensibility of the universe is a reflection of the structure of our own cognition. We are, in a sense, holding up a mental mirror and marveling at our own reflection. Karl Popper, on the other hand, saw science not as a process of discovering absolute truth, but as one of conjecture and refutation. We throw our best theories at the universe, and it tells us which ones are wrong. The fact that the universe consistently gives us clear, logical answers that it can falsify our ideas is what allows knowledge to progress. This very process of learning from our mistakes implies a universe that operates by consistent, knowable rules. A more modern, scientific take leans on the Anthropic Principle, Perhaps the universe is comprehensible for the same reason it has the right constants for life, because we are here to observe it. In a vast multiverse of possibilities, we inevitably find ourselves in a universe whose laws are stable enough and simple enough to allow for the evolution of intelligent, questioning life. A chaotic, lawless universe could not give rise to scientists, so our ability to do physics is not a miracle, it is a selection effect. We are the universe made conscious, examining itself. Yet, even this pragmatic explanation cannot completely drain the wonder from the situation. It still leaves us with the awe-inspiring reality that the cosmic code exists and that we, against all odds, are capable of reading it. This final defiance brings our journey full circle. It connects back to every other mystery we've explored. Our ability to grasp the probabilistic nature of the quantum world, the curved geometry of space-time, the silent puzzle of the Fermi Paradox, all of it is predicated on this one miraculous fact: the universe speaks a language we can learn. This isn't just a philosophical curiosity, it is the very engine of science and the source of our deepest inspiration. It implies that the cosmos is not an impenetrable fortress, but a grand, complex story waiting to be read. Every equation we write, every theory we test, is a conversation with the universe, and the most astonishing thing is that it talks back. This comprehensibility is the greatest invitation to explore, a silent promise that for every question we ask, no matter how bizarre or logic-defying the answer may be, there is an answer to be found. The universe's greatest defiance of our small expectations is its unwavering willingness to be understood. Reflecting on these 25 astonishing ways the universe defies our intuition, a powerful and unifying theme comes sharply into focus. The cosmos does not operate on a human-centered logic. It is not built for our comprehension, nor does it bend to our innate sense of how things should work. Instead, it runs on a set of deeper, often paradoxical principles that consistently challenge our most fundamental assumptions about reality. From the ghostly blur of the quantum realm to the unimaginable vastness of the cosmic horizon, these mysteries collectively paint a picture of a universe that is far stranger, more complex, and more wonderfully bizarre than we could ever have imagined from our limited vantage point on this pale blue dot. This journey through the illogical reveals a cosmos that is not merely a collection of objects obeying simple rules, but a dynamic, interconnected, and deeply mysterious process. The universe is not a static stage but an active participant in its own story, a story where particles communicate instantaneously across galactic distances, where time itself is a personal and elastic experience, and where the very fabric of space may be a holographic projection of information encoded on a distant surface. These are not minor curiosities or edge cases. They are central features of reality that force us to abandon a childish view of the cosmos and embrace a more mature, humbling, and ultimately more awe-inspiring perspective. They push the very boundaries of science and philosophy, blurring the line between the physical and the metaphysical, and demanding that we continuously refine our questions and our tools for seeking answers. This endless cycle of discovery is perhaps the most profound lesson of all. Each breakthrough, each answered question, does not bring us to a final conclusion. Instead, it peels back a layer to reveal an even deeper and more fascinating puzzle beneath. Unraveling the mystery of the atom gave us the bewildering world of quantum mechanics. Mapping the heavens led us to the shocking discovery of dark matter and dark energy. Our quest for understanding is an infinite regress of wonder, a perpetual invitation to keep looking, keep questioning, and keep marveling. It reminds us that intellectual humility is not a weakness but an essential virtue when facing the grand puzzles of the cosmos. To assume we have it all figured out is to close the door on the very wonder that drives science and philosophy forward. Ultimately, these 25 defiances are not a catalogue of failures for human logic, but a triumphant celebration of the human spirit. They showcase our incredible capacity for curiosity, our relentless drive to make sense of our surroundings, and our courage to follow the evidence even when it leads us to conclusions that seem utterly insane. The universe may defy our expectations at every turn, but it also consistently rewards our curiosity with deeper beauty and more profound mysteries. It invites us to keep looking up at the stars with wonder, and to keep looking inward at the nature of our own consciousness and perception with equal parts curiosity and awe. The greatest discovery is not any single fact, but the realization that the journey of discovery itself is endless, and that we are privileged to be a part of it here and now in this strange and magnificent cosmos. We've journeyed together through 25 astonishing ways the cosmos shatters our everyday intuition, from particles that exist in multiple places at once to the eerie connectedness of quantum entanglement, from the elastic nature of time to the silent, dominating presence of dark matter and dark energy. We've even ventured into the radical possibility that we might be living in a simulation. Each of these concepts pulls back a curtain on a universe that is far stranger, more complex, and more wondrous than our human senses and logic could ever have prepared us for. These aren't just abstract puzzles for physicists. They are profound reminders that reality itself operates on a level of sophistication that consistently defies our simplest expectations. This incredible voyage does more than just fill us with awe. It serves a deeper purpose. It humbles us. It shows us the boundaries of our current understanding, and in doing so, highlights the infinite potential for future discovery. The universe is under no obligation to make sense to us. It doesn't have to conform to our instinctive need for cause and effect, for solidity, or for a single, flowing timeline. Instead, it extends an invitation to think bigger, to question more deeply, and to continually refine our models of what is possible. Every time we think we have it all figured out, the cosmos reveals another layer of mystery, reminding us that the journey of exploration is never truly over. If this exploration has sparked a sense of wonder in you, if it's made you look up at the night sky with a new set of questions, then we've done what we set out to do. The conversation doesn't have to end here. Share your favorite cosmic defiance in the comments below. Was it the block universe, the holographic principle, or the terrifying silence of the Fermi Paradox that captivated you the most? Let's keep the discussion going. If you want to join us for more deep dives into the mysteries of space, time, and reality, be sure to subscribe and hit the notification bell so you don't miss what's next. Thank you for embarking on this mind-expanding journey. Keep questioning, keep wondering, and never stop being amazed by the incredible, logic-defying reality we are all a part of. The cosmos has surprised us before, and it is absolutely guaranteed to surprise